Hi everybody, welcome to this introduction to EvalC3 Online. This is our agenda this afternoon. The presentation has three main parts. In the first part of the presentation, I will discuss ideas around prediction and explanation and how EvalC3 can bridge both types of tasks. The second part of the presentation will be much longer. Here I will work through each of the steps in the workflow one by one. This includes importing and selection of data to be analyzed, the designing and evaluation of predictive models, how to view and compare the models that have been generated, and how to identify cases for follow-up with in-case analysis. Finally, in the third part of the presentation, I will outline some options you might then want to explore. These include different methods of analysis and a wide range of use cases. There will be 3 pauses for discussion during the presentation, as well as a discussion time at the end. During the presentation, please use the chat function to lodge your questions, which I will respond to during the discussion periods. In this slide, I want to talk about prediction and explanation as a useful background perspective on the use of EvalC3. Both of these are useful on their own and in combination. Historians pay a lot of attention to explanations of what has happened, but they don't do very much, if anything at all, in terms of trying to make predictions about the future. People investing in the stock market pay a lot of attention to trying to identify what might happen in the future and developing predictive models that can help them do that. Doctors are in the middle. They are interested in understanding the details of the causes of disease and how they can be cured, but they also want to know with some degree of certainty just how likely a treatment is going to work and in what circumstances. You have probably all come across the phrase, correlation does not mean causation. This is a warning to be careful about associations that you might find between events. But it is a warning that can be taken too uncritically. An association between events can often be of interest. It suggests that something might be happening. It can help us narrow our search to understand what is going on. We need to remember that in addition to the phrase correlation does not mean causation, it is the case that correlation or association is necessary for a causal process to be taking place. Necessary, but insufficient. Once we find an association, then the next sensible step to take is to investigate whether there is any underlying causal mechanism at work. Like related configurational analysis approaches such as QCA, EvalC3 tries to connect the process of developing good predictive models and identifying which of these are also good explanatory models. It does this by moving from a broad process of cross-case analysis into a more narrowly focused process of within-case analysis. Many of the steps that you'll see in the use of EvalC3 are about cross-case analysis, but they all lead up to the choices which will then inform useful within-case analyses. In these next 2 slides, I want to talk about 2 sets of ideas which have informed the design of EvalC3. The first of these is machine learning. Machine learning is basically a set of algorithms with a common purpose. An algorithm can be defined as an automated, reiterated sequence of operations applied to data. Typically these days they are implemented by a computer, but in the past also manually by people when carrying out something as simple as a long division. Machine learning algorithms are used to find patterns, such as clusters of things which have more in common with each other than they have with others, or predictors of things, associations between events which can be viewed as prediction rules, or exceptions such as those which do not fit predictive rules. EvalC3 provides 4 different algorithms that can be used to find good prediction rules, describing strong associations between events. The second set of ideas are those about comparative configurational methods. This includes methods such as QCA, or qualitative comparative analysis. What is attractive about this body of ideas is the rich view of the nature of causality. Events can arise not just from single causes, but from combinations of causes. And events can arise from more than one combination of causes. Causes can be necessary or sufficient for an outcome to occur, or necessary and sufficient, or neither but still likely. The absence of a causal configuration may not always be the cause of the absence of the outcome of the event. Other causes may be at play. And to complicate this picture even further, this set of ideas can be applied not only to understanding the causes of an effect, but also the effects of a cause. For example, the causes associated with a successful immunization program, or the effects arising from a cash distribution program. All these types of causes are potentially identifiable using a set of methods built into EvalC3, if they have been followed up by supporting within-case analysis. In this slide, I want to give a quick overview of the range of possible applications of the EvalC3 tools. EvalC3 can be used at least 4 different stages, as shown here: during project selection, during project implementation, during project evaluation, and for reviews of evaluations of such projects. For grant-making bodies, associations can be explored between the content of project proposals and the kinds of projects which are subsequently approved, or between the content of project proposals and their subsequent success. During project implementation, associations between participant characteristics and their experiences of workshops or training events can be explored, or the relationship between partner descriptions of their working relationships with others and the perceived success of those working relationships. In project evaluations, it is likely that the relationship between project activities and changes in people's lives will be of special interest, not only to identify the effects of those activities, but also the possible contributions of wider influences and activities, and the potential significance of what are called positive deviant cases, that is, outliers which are exception to the prediction rules that have been found. And on a larger scale, when reviewing the results of multiple evaluations, it may be useful to reanalyze the data that was generated, not only to confirm results, but also to make additional kinds of inquiries. Okay, we are now at the second stage of today's presentation, where I will talk about the EvalC3 workflow in considerable detail. The workflow can be divided into 3 broad stages. The first is data preparation, where you are formatting the data, uploading it to the EvalC3 website, and making some choices about what parts of that data you want to analyze. The second stage is where, having uploaded the data, you start to experiment with designing and evaluating predictive models. This is the engine room of the application, where all the hard work is done, computationally speaking. The third stage is where you have access to models that have been generated, where you can view listings of all the models that have been created, compare them to each other, and dive into detailed descriptions of all the cases covered by specific models. You will see in this slide I've circled the 3 stages. But you'll also see that there are some dotted lines which are used to indicate steps backwards in the workflow, where, having generated a model, for example, you then decide to go back and re-examine it, perhaps changing the data that it was based on, or tweaking the contents of the model and reviewing the performance measures once again. So I want to make it clear that the workflow is not necessarily a strictly linear process by any means. There can often be quite a lot of reiteration, involving redesign, review and revision. The starting point is here, where you register and log on to the EvalC3 website. The address link is shown in red. Hopefully you will have already registered and logged on before this event. If you have the possibility, please now log on and follow me as we work through the workflow. This will give you an opportunity to explore and experiment at each stage while you are listening to me, if you are any good at multitasking. Please do pay attention, before or after you have registered, to the Creative Commons license, the limitation of liability and the privacy policy. They are all important. Please also read the text at the bottom, which gives acknowledgement to all the people who have been involved in the development of EvalC3. When you log on, this is the first page you will see. In the center of the screen, you will have the option of uploading a data file of your own. At the bottom of the screen, you will see a list of all the previous files that you have uploaded, which you can click on and upload as needed. When you first start, there will be one file in this list called Crook 2010. This is the example dataset that is available to all users. Before you proceed, please pay some attention to the navigation aids. At the top right, there are two links which you can follow to get background information about EvalC3. You will find these links on every page. On the left side is the name of this stage of the workflow called Input Data. Next to it, you will see an information link about this stage of the workflow. On that help page, you will find details of the kind of data that you can import into this application. The minimal requirements of a dataset is that it is in CSV format. It has cases listed by rows and attributes of those cases listed by columns. In this slide, I will go into some detail about the kind of data that you can upload. EvalC3 uses categorical data, otherwise known as nominal data. This is data which has the value of 0 or 1, typically indicating whether a case has a particular attribute or not. The terminology to describe these attributes varies according to the field you are in. In the machine learning field, case attributes are described as features, whereas users of qualitative comparative analysis, QCA, describe attributes as conditions. In this presentation, I will use the more generic term of attributes. Nominal data can come from three different sources. Some case characteristics are nominal by definition. They are one type or another, such as an organization or a person still being in existence or not. Other characteristics, like city size, can be enumerated. Other case characteristics can be described using text descriptions. With numerical and text data, decisions need to be made about how to dichotomize the cases into two groups, which will be given values of 1 or 0. This can be done using methods which are driven by theory or driven by data. I won't go into the detail of those methods here, but more information can be found on this supporting website shown in red. This is what your data will look like when you have uploaded it. You will see your cases organized by row and the attributes of those cases organized across the columns, with the cell values of 0 and 1 indicating whether those attributes are present or absent. Just above the name of each of the columns is the default status of each column. The first column is always recognized as an ID column, and the last column is always recognized as an outcome column, and all the others are recognized as attribute columns. But these can be changed by clicking on those words to reveal a drop-down menu which allows you to change them, including the option to ignore a column. The only constraint here is that there must always be one and only one ID column and one and only one outcome column. There can be any number of attribute columns. Just above the data are two options to save the settings, either those which are already there, or if you have made some changes, to save these with a new settings name. Just above those options are 5 different descriptive measures of the data set as a whole. I won't go into details of those here, but you can see that there is an information icon next to each one which you can click on to find out what they mean. Just above this, on the right, is an option to click on Design and Evaluate, which is the next stage of the workflow. Next to that is an option you may want to use beforehand, which is to sort all the cases by configuration. What this does is sort all the cases into groups where the cases have the same set of attributes. A late edit to this presentation. The dataset you can see here is the Crook dataset, which is the example dataset built into EvalC3, as mentioned earlier. This dataset describes 26 countries named in the ID column on the left. The outcome of interest, described on the right-hand side, is whether those countries have a high or low level of women's representation in their national parliaments, indicated by 1 or 0. The other attributes describe potential predictors of the level of representation in national parliaments. They are as follows: electoral system, meaning the presence or absence of a proportional voting system; quotas, being the presence or absence of required levels of women's representation in Parliament. Women's status being a high versus low point on an internationally recognised measurement scale. Level of human development being a high versus low point on a UNDP index, and post-conflict situation, meaning the country is or is not in a post-conflict situation. We are now in the engine room of the application. This is the stage called Design and Evaluate. There are three main sections here. The first, on the left, is like a menu structure, where you can design a model through a series of choices of your own. The second is an evaluation section, which will automatically generate performance measures of that model. The third, on the right, is a search section, where you can use different search algorithms to find alternative good performing models. In the model design menu on the left, there are two subsections. The first is where you can choose whether you want to develop a predictive model for the presence of an outcome or the absence of an outcome. In this view, you can see that the user has chosen the presence of an outcome. Below that are listed all the attributes in your dataset which might be good predictors of that outcome. For each of these, you have a choice to select the presence or its absence, or for it to be ignored altogether as part of a predictive model you think might work. In this view, you can see that the user has chosen the combination of the presence of quotas and the presence of a post-conflict situation as a potential predictor of high levels of women's representation in parliaments. When you have made these choices, you click on the Save button below. In the Model Evaluation section in the middle, there are three subsections. At the top is a table called a confusion matrix. This describes the performance of your model in raw numbers. In the two columns are all the cases which have the presence and the absence of the outcome. In the two rows are the cases which fit your model at the top and those which do not fit it at the bottom. In the cells of the confusion matrix, there are the numbers of cases which fit each of the four possible combinations. In this view, you can see the results of the choices expressed in the menu on the left. In the top row, you can see that the model correctly identified the presence of the outcome in 6 cases, known as true positives. The zero value for false positives means it did not incorrectly identify any cases as having the outcome when in fact they did not. In the row below, you can see that where the model attributes were not present, there were 17 true negative cases, cases where the outcome was not present. But next to it, you can see that there were 3 false negative cases. These were the cases where the absence of the model's attributes suggests the absence of the outcome, but in fact the outcome was present. This indicates that we need more than one good performing model to account for all the cases where the outcome is present. Immediately under that matrix is a table summarizing whether your model is sufficient and/or necessary for the outcome to occur. In this view, you can see that the current model attributes were sufficient but not necessary for the outcome to be present. This is because there were no false positive cases. If there were no false negative cases, this would indicate that the model attributes were necessary. If there were no false positive or false negatives, this would indicate that the model's attributes were both necessary and sufficient. Further below is a section called Model Performance, which lists a number of prediction model performance measures, all based on the numbers in the confusion matrix. Each of the measures are useful in different circumstances, which are explained if you click on the link which says how to use. You can find out more about each of these measures by clicking on the information icon next to each measure. But a useful default choice when you're exploring different predictive models is the first one, called classification accuracy. In this view, it is 88%. If it was 100%, this would mean that there are no errors at all. In other words, no false positives or false negatives. On the right of this view, you can see the section called Search for New Models. This lists 4 different search algorithms which you can use to find good performing predictive models, either as an alternative to your manually designed models or as an approach to use on its own. You can click on any of the information balloons to find out more about these. They fall into 2 main categories. The first 3 find single best performing models using an exhaustive search, incremental search and evolutionary search algorithms. The decision tree search is different because it finds a whole set of predictive models which best account for all the outcomes, present and absent. Once a choice has been made about which search algorithm to use, simply click on Find at the bottom and then go to View Models using the button at the top right. We are now in the third part of the workflow. In this View Models view, we can see a full listing of all the models that have been developed so far, both those we have manually saved and those which were automatically saved by the search algorithms we have used. Each row describes a different model, including its name, when it was created, the way it was created, the various performance measures describing that model, and the attributes of the model itself. From this view, we can go in different directions. If we click on one row using the tick boxes on the left, we will be given 3 highlighted choices at the top right. One will take us back to the Design and Evaluate model, where we can look at the performance details again. Another will take us to a View Cases view, which we will look at shortly, to get a very detailed view of the cases covered by the model. If the model we have selected was generated using the decision tree algorithm, then the option to view that decision tree will then be highlighted on the top right. Or if we want to compare 2 or more of these models, we should select 2 or more of them on the left, then click the highlighted Compare Models button on the top right. Here you can see the first of 3 viewing options. This view shows the structure of a decision tree model. Imagine that a tree has fallen over on its side, and on the left-hand side of this diagram is the root of the tree, and on the right are all the branches and then the leaves. In the node at the root is the name of the outcome that the decision tree model is trying to predict. In this example, the outcome of interest is the percentage of women elected to national parliaments in 26 countries in Africa. The number 1 within that node indicates that the model is trying to predict the presence of that outcome. Each branch that goes out from there is a separate model predicting some of the cases where the outcome is present or absent. Each branch involves a combination of attributes, shown as nodes in the branch, which are necessary for that prediction model to work. The text above each node describes the attribute. In this example, they are attributes of the electoral systems and political contexts of the 26 countries. The number within each node tells us whether that attribute is present or absent. The 2 numbers below each node are taken from the top row of the confusion matrix. The first describes the number of true positives, that is, the number of cases which this combination of attributes correctly predicts the outcome. The second number describes the number of false positives, the number of cases where this combination of attributes incorrectly predicts the outcome. The percentage figure to the right of each node tells us how accurate the model is at that point in the branch. In this example, the performance measure is classification accuracy. When we look at this tree structure, we can see that there are 3 branches which predict the presence of the outcome, each of which is shown in green, and there are 4 branches which predict the absence of the outcome. There are 2 models which manage to predict a large number of the 26 cases. The first is the branch at the top that tells us where there are quotas for the number of women in Parliament and the country is in a post-conflict situation. Then there are 6 countries in this category and all have high levels of women's representation in Parliament. The second branch tells us that where quotas are absent and women's status in these countries is low, then there are 12 countries in this category and they all have low levels of women's representation in Parliament. Above the tree you will see a row of performance measures describing the performance of the tree structure as a whole, in other words the whole set of 7 models described by the 7 branches. To learn more about these and how to view the decision tree, click on the help link at the top left. The second viewing option is to compare 2 or more models that have been saved. In this view, cases are organized by rows and models are organized by columns. For each case, its status in each model is color-coded according to which of the 4 categories in the confusion matrix that case belongs to. These are the true positives, false positives, true negatives, and false negatives. Where the case has the same color in each model, this means the models are in agreement about that case. Where they are different, the models differ in their view about the status of that case. These agreements and differences have significance in terms of where we might want to go next in terms of doing within-case investigations of possible causal mechanisms that might be at work. If a case is seen as a true positive by 2 different models, then it would be worth investigating this case to find out what evidence there is in favour of one model versus the other. Where there are many of these types of cases of the same status, we will need more information in order to prioritise which of these to investigate in detail. Looking down at the bottom of this view, we can also see some summary statistics describing each of the models. These describe 3 different forms of coverage, the extent to which the models identify the expected outcome. The first is raw coverage, the percentage of all the expected outcomes which are identified by each model. The second is unique coverage, the percentage of all cases where the model alone has correctly identified the outcome. The third is aggregate coverage, the percentage of cases where the 2 models combined have correctly identified the outcome. These figures suggest the extent to which we can see the 2 models as complementary versus competitive. View cases is the last of the 3 possible views. This view is useful for thinking about case selection for within-case investigations in more detail. Like the previous compare models view, this view lists cases by rows and lists the status of each model in terms of the confusion matrix categories they belong to. In addition, it displays all the attribute values of each model. There are also 2 additional measures which can help with case selection. The first, which is already displayed, is the 5th column labelled similarity. This shows the extent to which a case is similar to all the other cases in the same confusion matrix category. A high percentage value means high similarity. So, if you wanted to examine a case which is very representative of all the cases in its category, you would select one with a high percentage. Then, if you wanted to test out how generalizable any findings from that case are, you might select a case with a very low percentage measure of similarity. The similarity measure here is based on a measure which counts the number of matching values for the attributes in 2 compared cases. The second similarity measure comes into operation when you tick one of the boxes in the first column. This will then display some color-coded case measures in the 3rd column. Green-colored cases are those which are most similar to the case you have selected. Brown-colored cases are those which are most dissimilar. This measure is different from the first in that it compares all the cases across all the confusion matrix categories, not just within one category. But it can be used for the same type of case selection purpose to identify similar cases and most different cases. to find both the differences and similarities between these. Up to now, I've only made a brief reference to the rationale for doing follow-up with in-case investigations. This rationale can be elaborated into 4 more specific purposes. The first is to verify that the attributes used to describe the case have been accurately applied, that is, to make sure that there is no measurement error involved. The second is to provide an illustration of the events in much more detail than that simply given by the names of the attributes, which are a part of the model. The third is to provide an in-depth explanation of the causal mechanisms linking the 2 or more attributes of the case which are good predictors. The fourth is to explicitly look for contradictory evidence, in particular confounding factors, that is, background factors which could be a cause of both the attributes in a model and the associated outcome. It's important to note here that these rationales can be usefully applied not only to a within-case investigation of true positive cases, but also to the other 3 categories of cases: false negatives, false positives, and true negatives. A more detailed explanation of the possible ways of doing follow-up with in-case investigations is available on the supporting website shown on this slide. This webinar was designed with the intention of being an introduction to the use of EvalC3. While it has been quite detailed, there is a lot more that can be done in terms of exploring its possible applications. Here are some of the options that might be of interest. Firstly, if you have data sets which you can access, you can experiment with those. Secondly, you can experiment by reanalyzing existing data sets, such as those available on the compass.org website. Thirdly, there are also ways in which you can elicit tacit and informal predictive attributes and models from people involved in interventions that are being evaluated. With any data set, you can experiment with different ways of doing data dichotomization and attribute selection. Having identified some good performing predictive models, you can then explore case selection strategies that would be most useful for within-case investigations. Finally, you can consider different options for testing out your findings with stakeholders who have their own case-specific knowledge. I can provide some help with some of these and other tasks via the EvalC3 email list, or on a more in-depth, customized and paid basis. In this second last slide, I'd like to acknowledge all the people who have contributed to the development of EvalC3 Online. This includes Sports England, who have funded its development, and a team of people at Sheffield Hallam University, led by Dr. Katie Sheehan, who are all part of the Sheffield Hallam University Advanced Wellbeing Research Centre. The app is based on the original Excel version coded by Mark Skipper at Activate, which is based on my 2017 design. That design is available for use under the terms of a Creative Commons license as described here. Finally, for the purposes of our discussion in the time remaining, I've reproduced this slide showed earlier listing the range of possible use cases for EvalC3.